Namaskara. We will go through the theory of magnetism, electromagnetism and electromagnetic induction. In that respect, the magnetism comes to the presence of a magnet which is supposed to have north pole and south pole. It has been assigned. The presence of the magnetic field is represented by the lines of force. That's nothing but this. The lines of force spreads out when it comes over here. However, they are totally inside, confined in this portion. It is this way. The flux is assumed to be coming out and entering into the north pole, coming out of the north pole and enter into the south pole. If I keep piece of iron here, it is attracted. On the other hand, if I keep a piece of iron, it may not be attracted. In that respect, this iron piece is in the magnetic field while it is not so. So there is always a boundary up to which the magnetic field exists. Beyond that, the magnetic field is not there. It need not be an iron piece, it can be a magnet also. If I have a north pole and south pole placed, magnet having north pole this side, it experiences a force of repulsion. On the other hand, if I place a north pole and south pole faced magnet here this way, it will be attracted by this, indicating like poles repulse each other and unlike poles attract each other. These lines are at the same time, the lines of force will be continuous, it is not discontinuous. The magnetic field experienced here is less, while magnetic field experienced is more, because the lines of force are more here, lines of force are less here. With that, the lines of force is called the flux. The group of lines of force is called the flux, the unit being Weber, denoted by this. The density is nothing but, or the flux density is nothing but flux per area. If I consider a area of say some A here, the flux density here is obviously B is equal to phi over A, the unit being Weber per meter square. However, it has been replaced by Tesla, denoted by capital T. The flux density here, if you consider, the flux density is more here, while the flux density here is less. The field strength of a magnet cannot be increased or decreased. However, when you go for an electromagnet, it can be done so. Consider a conductor carrying current. This is I. It has been found that whenever the conductor, if at all we think of a cardboard, and the wire is placed here and the iron filings have been spread here, it has been thrown on the cardboard. When the current is made to flow through the conductor, it has been found this aligns itself in a particular pattern, indicating that there exists a magnetic field. What's the direction of the magnetic field, or what's the direction of the flux produced? In that respect, if this is the conductor, go for the hand rule, right hand rule. Hold the conductor in the right hand with the thumb showing the direction of the current. That's nothing but this. The folding of fingers or curling of fingers will give the direction of the flux produced. Obviously, it will be this way. This is the flux. As the magnitude of the current goes on increasing, the flux produced also goes on increasing. The field here is more. As we go away from this, the field goes on getting reduced. If the conductor were to carry the current in the opposite direction, then the direction of the flux produced will be this way. Hold the thumb in the direction of the current, that's downward. This gives you the direction of the flux produced. With that in mind, this will be the flux produced. Every time the conductor cannot be shown to be a straight line like this. In that respect, some method of representing the conductor, the direction of the current, and also the flux produced must be considered. In that respect, think of a conductor. This is the conductor carrying current I, and consider this one to be the observer I. What's the direction of the flux produced? As such, it can be seen here now. This is the direction of the current, so therefore the flux produced must be this way. This can be indicated schematically like this. The conductor is represented by a circle. When it comes to the direction of the current, arrow is considered to be the reference. Arrow will have a sharp end or the point, and the other end is generally called as fletching or flight. Generally this is made of plastic or it may be feather. As the observer looks at this, he looks at this fletching end or the flight end, in which case it is represented by a cross. What's the direction of the flux produced? We can go for either right hand rule or right hand cross rule. Hold the thumb in the direction of the current. The current is going into the plane of the paper. Therefore, this must be the direction of the flux produced. So, with that in mind, so this is the direction of the flux. On the other hand, if the current were to be coming towards the observer, this is I, this being the arrow, this is the conductor. The observer will look at the sharp end or the point, which can be denoted by a dot here. The direction of the flux produced is obviously this way. Hold the thumb in the direction of the current, that's this one. This gives you the direction of the flux produced, thereby it is this way. This is the flux. It can also be considered by considering the screw rule. In that respect, you have a look at this slide. Here you can see the conductor. The right hand is the conductor is held by the right hand. This is the thumb. This gives you the direction of the current. This gives you the direction of the flux. The right hand screw can also be considered here. Turn the screw in the direction of the current. The direction of turning gives the direction of the flux. Since it is in this way, it's also, you can see, the same thing has been shown here. It has been shown over here. On the other hand, here it is, the current is in the opposite direction and the screw is being rotated in the anticlockwise direction. The screw is coming back or it is being rotated this way. That's in that respect, you can see here now the direction of the flux is the opposite direction. This is what has been shown here. The screw has been shown here. This is the conductor. The arrow is coming towards the observer. That has been shown here. Now in order that the screw should come out, or it should be in the direction of the current, or it should come towards the observer, it has to be turned this way. That's nothing but this is the direction. The same thing has been illustrated here by the right hand. The other one is current is going away, so that's nothing but this here. The screw has to be turned this way so that the screw goes into the object. As I said, the flux produced here, this is the current, the flux produced is less, and this is the current. This is the current and this is the flux. The flux produced is less. How to increase the value of flux produced, or how to increase the magnetic field? in that respect, as I said, the current increases, the flux also increases, but the current cannot be made exorbitantly large. In that case, some other method must be made. If it is coiled, then what happens? Let us see. The coil has been, the conductor has been coiled like this. With that, if the current is this way, the current is coming here. What's the direction of the flux produced? Hold the thumb in the direction of the current. This gives you the direction of the flux produced. Therefore, the flux produced will be inside here. When the same current comes here, what's the direction here now? It is like this. Therefore, again the flux will be in this direction. This gets added up. With that, the total flux will be something like this. The flux inside this portion, that's nothing but this portion. This is nothing but inside of the coil, generally called the core. Obviously increases. Once the flux inside that increases, the flux density inside the core also increases. So that you can see here with respect to this. You can say the flux carried by the conductor, the flux produced by the conductor at different points has been shown here, and they get added up. So finally, the resultant will be this. You can see here the flux is coming out of the coil, and whenever the flux is coming out of a particular part, it acts as a north pole, while here it is south pole. Here we can observe the core is made of air. This is called as air core coil. This is one turn. This is the second turn, like that it goes. Whenever the conductor is coiled, the flux produced increases. Thereby, the flux produced not only depends upon the current that is passing through the coil, but also depends upon the number of loops that we have here or number of turns we have here now. So thereby the flux is proportional to, or it is equal to, the product of current and number of turns. This is proportional to the current and number of turns. This is what's called as the ampere. Unit of I is ampere and N is nothing but turn. Turn being a dimensionless quantity, it is generally left out. The product of these two, or product of current and the number of turns, is called as the magnetomotive force or MMF, which is similar to the electromotive force in case of DC circuits. This can be written as equal to, flux will be equal to IN over the constant of proportionality can be taken as the reluctance. This is the reluctance. What is reluctance? This is the opposition to establishment of flux or the production of flux. This is very much similar to the resistance in electric circuit. What is this resistance? As you are aware, it is rho L by A. In the same way, what will be the reluctance? As the length of the coil goes on increasing, the reluctance path also goes on increasing, opposition also increases. Therefore, the reluctance is proportional to the length also. At the same time, when the area goes getting reduced, the opposition also goes on increasing. Therefore, the reluctance will be inversely proportional to the area. Thereby, we can say S is equal to L over A into mu naught mu r. The constant of proportionality is nothing but the mu naught mu r. This is resistivity, length of the conductor or length of the current path, area over which current is flowing. Here it is length of the flux path, A is the area over which flux is flowing, mu naught is the free space permeability, and that is taken as 4 pi into 10 to the power of minus 7 Henry per meter. On the other hand, mu r is the relative permeability. So this relative permeability can be thought of the ease at which it allows the flux to pass through it. What is that? in that respect, let us say I have a coil placed in the vacuum. With certain amount of current, it produces flux. The flux produced will have some portion, and that is decided by the permeability of the media. That's nothing but the vacuum, and that has been taken as 4 pi into 10 to the power of minus 7. The classical vacuum. When it comes to mu r, it is nothing but the relative permeability. If the same coil is wound on a iron piece like this, the flux produced is more, in which case the mu r is called as the relative permeability and is always greater than 1. With this, what will be the value of, or what will be the flux direction of the flux produced by the coil, or generally called as the solenoid. In that respect, we can have a look at this. Think of a core, and that you wind the coil like this. This is the applied voltage. The current is flowing here. The current goes this way. It has been wound like this. Current goes this way and it comes out here. This is the, you can call it as the solenoid. If it is a conductor, we hold the thumb in the direction of the current. The curling of fingers will give the direction of the flux. This is nothing but the thumb is in this direction. On the other hand, when it is coiled like this, it has to be reversed. What's that? Hold the fingers in the direction of the current. The thumb will give the direction of the flux produced. Here, the current is going this way. Therefore, this is the direction of the flux produced. Thereby, this is the flux. Therefore, this acts as a north pole while this acts as a south pole. Consider the same coil and assume the current direction is changed. With that, the current here comes this way. Therefore, what will be the direction of the flux produced? Now, hold the fingers in the direction of the current, that is this one. This gives you the direction of the flux produced, that is this. This is flux, this is north pole, while this is south pole. We will observe, having wound the coil in the same direction, changing the direction of the current will change the polarity of the poles. The coil need not be wound in the same way, it can be wound in the other direction also. For example, if it is wound this way, with respect to the polarity of the battery here or polarity of the cell, the current is same, but the direction of the current now will change. It will be this way. Therefore, the direction of the flux produced is like this. This is north pole and this will be south pole. So, the direction of the or polarity of the pole can be changed by changing not only the direction of the current, but also the direction in which it has been wound. And that has been illustrated here. You can see here the current is flowing down, the fingers are also downward, and the thumb gives the direction of the flux produced. Here the direction of the current has been changed, the polarity of the poles also have changed. The field intensity is nothing but the defined as H. H is nothing but ampere turns per unit length. That's nothing but equal to mmf by L, or mmf per meter is generally taken as the field intensity. Then reluctance we have already studied, or we have already gone through it. Now what will be comparison between the electric circuit and the magnetic circuit? When it comes to electric circuit, it is defined as the path in which the current flows, while magnetic circuit is the circuit in which the flux follows the path. That's the difference here. Now, electric circuit is defined as the path of the electric current, while magnetic circuit is defined as the path of the magnetic flux. Here we have the voltage, R EMF, R potential, all are one and the same. Here this is the unit is nothing but volt, while here this also called as MMF, this also called as EMF, while here it is MMF. The unit being ampere. However, because the MMF also depends upon the number of turns, it is generally taken as ampere turns. Often you come across the term ampere conductors. Generally in electrical machine design, ampere conductors are considered. So in order to distinguish that, it will be mentioned as ampere turns or ampere conductors, though the unit of this one is only ampere. Opposition to flow of current is resistance. Opposition to flow of current is resistance, while opposition to flow of flux is reluctance. R is rho L by A, while S is L over A into mu naught mu R. The current here, this is V by R, while flux is ampere turns divided by the reluctance. It's not, though this T stands for the Tesla, it is not Tesla when it is associated with this. It can be written as AT by S also, or it can be written as MMF by the reluctance S. Then when it comes to the current density, generally denoted by delta or J, this will be equal to current divided by the cross section of the conductor, while here it is the flux density. This is nothing but the flux divided by area. Like conductance, conductance is nothing but 1 by resistance, while here it is called as the permeance, generally denoted by lambda, and this will be equal to 1 by the reluctance. When it comes to the electric circuit, insulators are available to insulate the electrical parts. When it comes to magnetic circuit, there are no magnetic insulators. However, magnetic shields are available to divert the flux path. To maintain a current in a circuit, electric energy is required. However, once the flux is established in a magnetic circuit, there is no expenditure of energy coming into picture. So this gives some idea about the comparison between the electric circuit and the magnetic circuit. Next, we will go for electromagnetic induction. Electromagnetic induction refers to the generation of voltage in a coil. And what is that? To understand that, we can go for a coil and connect it to a galvanometer. Think of a permanent magnet. The presence of the magnetic field is represented by the lines of force here, this way. When there may be some more lines also here, this way. When the magnet is suddenly pulled this way, there will be a deflection in the galvanometer indicating there is a flow of current here or there is an induced EMF here. So long the magnet is moving, there will be a deflection in the galvanometer. Once the magnet comes to standstill, the deflection will be zero, or the flow of current is zero, or the force that is responsible in driving the current is also zero. If the magnet is moved away from the coil, again the same phenomena exists, or the deflection will be there and continues to exist till the magnet is moving and comes to zero when the magnet comes to standstill. This is the field, or you can say the magnet. So with that, when the magnet is moved this way or that way, you will observe a deflection in the galvanometer. Keeping the magnet stationary, move the coil this way or that way, again there will be a deflection in the galvanometer, indicating so long there exists a relative motion between the two, there will always be induced EMF. Instead of this being a magnet, if it were to have been a wooden piece, if I move the wooden piece this way or that way, there will not be any deflection in the galvanometer, indicating wood is not cannot convert or cannot cause an induced EMF in the coil, while a magnet can do it. In that respect, the flux is responsible in inducing the EMF. What is the reason for the induced EMF in the coil? It is because of the change in flux linking with the coil. That's the reason. So Faraday found that because of the change in flux linkage, there will be an induced EMF. Thereby, he concluded in the first way, whenever there is a change in flux linking with the coil, there will be an induced EMF. That's the first one, Faraday's law. The second law, the EMF induced is proportional to the rate of change of flux and also depends upon the number of turns. That gives the magnitude. So thereby, the EMF induced is generally taken as N, change in flux linkage, change in flux is nothing but d by dt. Often this is also written as, what is this flux linkage? This is nothing but the product of flux into number of turns is taken as the flux linkage. N being a constant, you can write this one, it can be taken out from this part and it can be written as equal to N d phi by dt. So the induced EMF can happen because of so many reasons in that respect. E is equal to N d phi by dt. The induced EMF depends upon the N. It depends upon the flux also, magnitude of the flux also. It depends upon the rate of change of the flux also. And at the same time, if you have, say, a coil moving from one magnetic field to, this is one magnetic field, this is another magnetic field. Whenever the coil traverses from one magnetic field to another magnetic field, it may be conductor. Many a times, the conductor, coil, turn, loop, circuit, winding can be interchangeably used also. So with that in mind, when the circuit or the conductor moves from one magnetic field, strength of one magnetic field to another magnetic field, there will be an induced EMF also. If at all the coil changes its shape, for example, let us say I have a circle through which the flux is passing. If at all it changes its configuration, if loses its shape, it may become something like this also. Again there will be an induced EMF because there is a change in flux linkage. So with these things in mind, consider what will be the change in flux linkage when the conductor is moving in the magnetic field. The flux always comes out of the north pole and enters into the south pole. This is the flux. Consider a conductor. This is the conductor. If at all the conductor is moved this way or this way, the flux linking with the coil will be, the change in flux linkage will be 0. It may be something like this. Let us say these are the hot wires, steel wires. If I am moving this way without coming in contact with this, the number of burning marks I get is 0. Same hot wires, lengthwise is enormous, it is infinitely long, and also here also infinite number of hot wires are there. Similarly, consider one more case here now. If I move this way, what will be the number of burning marks I get? What will be that here now? In that respect, here the burning mark is 0, here it is maximum, while here it is more than 0 but less than maximum. Instead of these being hot wires, assume they are the lines of force and the conductor is moving this way. This is nothing but the flux lines, and this is the conductor. As it moves this way, it is not cutting any flux, or there is no change in flux linkage. Therefore, when E is equal to N d phi by dt, when the change in flux link or when the change in flux or change in flux linkage is 0, the induced EMF is also 0. Here it is maximum. In that respect, the induced EMF is more than 0 but less than maximum value, while here it is maximum. So with this in mind, you can see here now there is no flux linkage, therefore the induced EMF is 0 here. On the other hand, think of one more case. Let us say I have the same pole field. The conductor is placed here and it is not moved at all. When it is not moved, though the conductor is in the magnetic field, there will not be any induced EMF. Here it is E is equal to 0, here also it is E is equal to 0. Consider another case. This is the conductor. When it is moving this way, the flux linking with the conductor is changing, or the conductor is supposed to be cutting the flux. Therefore, the induced EMF here is maximum. If the conductor moves downward, the same thing happens, the induced EMF will be maximum. What will be the direction of the induced EMF? In that, before I go for that, you can see here in this one, the conductor is stationary. To the conductor, a galvanometer has been connected. Therefore, since it is not moving, the relative motion between the magnetic field and the conductor is 0, no induced EMF is also produced. When the conductor is moved horizontally, that means parallel to the lines of force, the induced EMF is 0, the galvanometer reads 0. In the third case, you can see the conductor is being moved upward. Obviously, there is an induced EMF. While here, the conductor is moving downwards, again you will observe a deflection in the galvanometer. With all these things, what will be the direction of the induced EMF? To understand that, when the conductor is moving upward, how to find out the direction of the induced EMF? In that respect, Fleming's right hand rule or Lenz's law can be used to find out the direction of the induced EMF. First, I will go for the Fleming's right hand rule. Go for this the right hand. The forefinger gives you the direction of the flux produced. This middle finger gives you the direction of the induced EMF, and the thumb gives you the direction of the conductor in which it is made moving. This is the direction of the flux. The conductor is moving upward, therefore the induced EMF is towards the observer or coming out of the board. Coming out of the board means this becomes positive and this becomes negative. If at all it is given a closed loop, if the conductor is provided with a closed loop like this, let us say it's a galvanometer, then the current starts flowing this way. Remembering the direction of the induced EMF and the direction of the current coming out is same. Both of them are one and the same. The current comes out of the positive terminal of the polarity for a generator. On the other hand, if the conductor were to be moving down, then what will be the direction of the induced EMF? To understand that, now the conductor is moved down. This is the flux, this is the direction of the motion or the direction of the conductor in which it is moving, therefore the induced EMF is in the opposite direction. Now the current is going away from the observer, or this middle finger shows the positive terminal of the source, and that's nothing but this becomes positive and this becomes negative. Therefore the direction of the deflection, if it were to have been this way, when it is upward, it changes in the opposite direction. This can be seen with reference to this also. This is the thumb, motion, field or flux. This is the middle finger, induced EMF or current. The same thing can also be when it comes when there is a difficulty in writing the hand on the sheet or on the board, you can go for this also. So this is nothing but the schematic representation. This is the thumb, and this is the middle finger, the forefinger, and this is the middle finger. This is nothing but the thumb showing the direction of motion. This is the forefinger showing the direction of the field or the flux. This is the middle finger showing the direction of the induced EMF, or it can be current also. And that is what has been shown here. This is the graphic representation or schematic representation of the Fleming's right hand rule. And here we can see here the thumb is in the direction of the motion, forefinger is in the direction of the flux, and the middle finger is in the direction of the E. And this is in the opposite direction. So instead of showing the right hand, it has been schematically represented here now. This is the representation of the right hand, where the thumb shows the direction of the conductor motion or direction of movement of the conductor. Forefinger is showing the direction of the flux, that's nothing but this one, and this is nothing but the direction of the induced EMF, that's nothing but the middle finger. In which case this becomes positive and this becomes negative. What is this Lenz's law? When the conductor is not provided with any closed loop, there is an induced EMF, but there will not be any current. If it is provided with a closed loop, then it circulates a current. As such, the direction of the current setup will always be such that it opposes the cause. What's the cause? The cause for the conductor or the EMF induced is the motion. So this motion must be opposed. In order to oppose this motion, what should be the direction of the current in this conductor? Or the force must be in this direction. This must be the opposing force. In order that the opposing force to be like this, what should be the direction of the current in the conductor? For that, generally what's called as the Fleming's left hand rule is used, where the forefinger gives the direction of the flux, that's nothing but this. The conductor is moving up the force, that's nothing but this is the force that is required. The conductor is being moved this way, so according to Lenz's law, it should oppose the cause, therefore the force must be in the opposite direction, that's nothing but this one. So in order that the flux to be this way and the force to be like this, the current must be away from the observer, which is nothing but this. So thereby the direction of the induced EMF here in the conductor can be found out either by considering the Fleming's right hand rule or Lenz's law. In order to give a better idea about the Lenz's law, consider this example. I have a magnet, an electromagnet, a coil connected to a source becomes an electromagnet. The source may be DC or AC. When it comes to DC, it behaves like a permanent magnet. When it comes to AC, it will be behaving like a magnet but changing its polarity for a very half cycle. This is nothing but the voltage, it circulates a current I here. This is nothing but the direction is this way, therefore the flux produced is like this will be the direction. This is the north pole. Let us say I have a coil here. I have a coil wound in some way this way. When I move the magnet suddenly this way, there will be an induced EMF. In that respect, what will be the direction of the induced EMF? In that respect, now Lenz's law comes into picture. Since the magnet is coming towards this coil, this should establish a current such that this movement is opposed. This movement will be opposed only when this side of the coil becomes north pole. In order that this to be the north pole, the flux must be like this. In order that flux to be this way, what should be the direction of the current? Now hold it like this. So therefore, this must be the direction of the current. Therefore, here you can see the current enters here, comes this way and comes out here now. Now this acting as a source now, therefore this must be positive polarity and this must be negative polarity. So this is how the Lenz's law can be explained also. You can see here the magnet is coming towards another coil, direction this is coming, this is north pole, this is opposing that, and there is here the current is in the, of course this is current is coming out of the coil, means this should have been positive and this will be negative. It acts as a source, therefore the current is coming out of the coil. This is the magnet is being now pulled away from that. When the magnet is being pulled away from that, that means when it is being pulled this way, this should not be allowed to move away. In that case, this should become south pole. In order that this becomes south pole, the direction of the current in this must change, and that is what you can see here, that has been shown here, so that this becomes north pole. So with all these things in mind, we can say the induced EMF will be, Faraday says only the magnitude of the induced EMF, that is nothing but n d phi by dt, and Lenz's law says it should always, the induced EMF must always oppose that one, therefore that opposition is indicated by this negative sign. We can conclude the induced EMF in a conductor can be along both magnitude and direction wise, n minus d phi by dt. I will stop here. I will continue in the next class.